I'm very, I'm very excited about our guest speaker today. Sarah Tepfer is with us. She was a former Star 140 GSI for many years. She's got a really unique interdisciplinary background that combines both sciences and design. After receiving a Bachelor in Science and Chemistry, Sarah came to UC Berkeley and was in both our MArch and MS program here in the Building Science, Sustainability, and Technology area, in which her thesis was about documenting current practices for integrating material health evaluations into the design process. She's currently a consultant with Arup, and she's also now in the doctoral program at Harvard in their Graduate School of Design. So I have been delighted to stay in touch with Sarah and was thrilled when she agreed to come back to 140 to give this lecture. She has so much to offer us. So I would just like to welcome her. I am going to mute now and hand it over to Sarah. Sarah, are you able to unmute yourself? Great.
I'm audible. Good. And you can see my slides? Okay. I'm going to assume yes. All is good. And thanks, Gail, for that introduction. That's really generous. As Gail mentioned, my background is really in chemistry and architecture. And a lot of my work at Arup kind of sits in between those things. So often my role on projects is to inform the team's design and material selection based on how materials are impacting human and environmental health. And I thought I'd share some of that with you today, in addition to some just touching a little bit on healthy indoor air quality and some topics there. So let me see here. So today, just a little very brief outline about materials, kind of orienting you to what all of this is all about. It's a pretty broad field and there's a lot changing. So I thought I would just give you a little introduction there and talk about why it is architects are caring about this. It's, I think, a little bit surprising that health and materials aren't already kind of assumed. So why is it that architects are even coming into this conversation? And then a few case studies of where I've had an opportunity to work on some projects that have done some really great things, in addition to some other projects that I didn't work on, but I think are pretty great exemplars. And then lastly, talking about kind of how the materials and health conversation fits into some other topics that you may have heard about. And then touching on healthy indoor air quality. So while the materials selection topic is really about kind of source control in indoor air quality, there are other aspects of IAQ that are just as important to discuss. So hopefully something in here interests you and you find it informative. And if you have any questions, I think Gail and the GSIs will be monitoring the chat, so feel free to jump in there. Or if you want to just jump in verbally, go ahead and do that too. I really appreciate questions. So yeah. So we're going to start with a poll everywhere question just right off the bat. So I think that you've done this before and know the drill, but I just was curious what comes to mind for you when I say, what is a sustainable material? What words come to mind? And we'll generate a nice word cloud just right off the bat. So if the instructions aren't clear to you, just text Gail Britter 190 to 37607 and
so this is what we did before with one of the passive cooling polls. So the screen should be showing content. I'm not seeing anything up yet, but let's hope that this is working. GSIs, if you can go ahead and do that as well, and that'll allow us to check. Oh, there we go. Yay.
Yay. I was about to test it. I was about to send my own words. That would have been no fun. So I can see that you've had an embodied carbon lecture. I see healthy is on there. That's great.
And it's interesting, I'm seeing that people are both putting in a type of material. I see bamboo, I see wood, and I also straw. I also see that people are putting in what is it that makes a material sustainable. So the
Yeah,
criteria. So this is great.
yeah, I love to see the diversity here. And we'll definitely touch on a lot of the topics that are kind of defining, like Gail said, some of the things that make a sustainable material. And yeah, I don't know why Peter's in there, but
Okay, so I am going to stop my share, which means Sarah, you can now go back to yours. And
great.
I'm pretty sure that you're able to do that yourself.
Yep, you should be seeing my screen again.
Great. That worked.
Good.
Yay.
You never know. Great. Okay. So great. So here I have kind of a swath of materials that you might be used of insulation materials. So let's say you were tasked with identifying a sustainable insulation material for a project. And so I think we've kind of talked about a lot in the word cloud of what aspects might kind of define a sustainable material. So first, you've probably had R value beaten into you like crazy, and you're sick of talking about it at this point. But that's definitely an aspect of sustainability, is how it performs. Definitely cost. I don't know if that was in our word cloud, but cost is definitely an aspect of sustainability. I think this is very true in the words that we saw, that embodied energy, global warming potential, those came up as important aspects to consider. But I would argue that there are a few other considerations that we need to think about as we consider sustainability in materials. So we've got does it work, what's its cost, we've got how it's made, and whether that has implications for embodied energy and global warming potential. And I would say we would also need to think about kind of what's in it. What are the chemical contents? What do those chemical contents do from a human health perspective? How much of those chemicals, if they are hazardous, how much are there? And in what concentrations? And are there exposure routes from those chemicals to us? So I think what these are all really asking is, does this material pose a health risk? So I saw the word healthy in the word cloud, which I was very excited to see, because I think healthy is a really important aspect of materials and sustainability. And I think what we're really asking is, how do materials pose health risks? And I wanted to stop and pause a little bit on what risk can mean, because it's kind of a tricky term. And I thought I would do that with a little example, using roads as instead of chemicals, because I think it's a little bit more tangible. But we can think about risk as a function of both hazard and exposure. So if we think about hazard first, we can think about kind of the toxicological properties, or the degree to which a circumstance or a chemical substance could have a negative effect. So in the example of these three roads, obviously my walking down a gravel path will have very different negative effects than my walking across Interstate 80. That will affect me very differently, or have very different toxicological properties. We can think about the time scale of the effect when we think about hazards. So we can think about how long will that effect last. If I skid my knee on this path, that'll be really different than if I get hit by a car moving at 80 miles an hour. That time scale will be very different. And we can think about potency, or that meaning the amount of some interaction that is required to have a negative effect. Very different from in the case of, a rickshaw moving slowly in Mumbai versus a car moving at 80 miles an hour on a freeway. We can also think about exposure. And when we do so, we think about frequency. So how often am I crossing the road? How often am I interacting with chemicals of concern? We can think about the intensity of the interaction. So am I crossing the road at the ground level, or am I crossing over a bridge, as I was when I took this photo? And in the context of chemicals, so the intensity of the interaction being whether it's, breathing a dilute mixture of chemicals of concern versus licking them of a highly concentrated block. And then we can think about duration. So how long is spent in the hazardous environment. So am I spending 5 minutes crossing a road versus spending 20 minutes? Each of these has implications for the risk that is posed. And conventionally, we want to think about how do we minimize risk, first of all. And conventionally, when we think about that, it's typically been we want to minimize the exposure. So if we minimize exposure, we're putting on PPE, we're protecting ourselves, we're preventing any source of exposure from coming into our bodies. But we do know that exposure happens. So even when we seek to minimize the exposures, they do occur. So a different train of thought would be, how about we minimize the hazard? And when we do minimize the hazard, we can say, okay, then exposure really doesn't matter. If we're working with safer chemistries in the first place, then we don't really need to worry about exposure. We can know that we're minimizing the risk just through minimizing hazard. And this is kind of the train of thought that has really guided and informed architectural decision making. So the hazard-based approach is really what has kind of surfaced as the kind of dominant way of thinking about risk minimization in practice. So when we think about risk in hazardous materials and buildings, there's a lot we can think about, and there's kind of this kind of overarching way of thinking about hazardous materials called the 6 classes for safer chemistry. And 6 classes are just 6 classes of chemicals that are known to be hazardous. So first off, halogenated flame retardants. You might have heard of these. They're often found in foams, in electronics, in flooring materials like carpet padding, in cushions and insulations. And the issue with these is that they're persistent and carcinogenic or cancer causing, which obviously is not such a great thing. We can also look at phthalates and bisphenols. So phthalates are often used to make rigid plastic soft. So anytime you have a PVC material that's actually soft, it probably has phthalates in it to impart that property. And these are really often found in sealants and adhesives, in floorings, in electronics, in like leather, fake leather. And the issue with these is that they're endocrine disrupting, which means they interfere with hormone regulation, which has, as you could imagine, pretty dire consequences. We can also look at antimicrobials, and those are often found in materials that are going to be highly frequently touched, so like countertops, furniture, surface coatings like paints. And what's interesting about these is that you might expect that they are doing something good, right? They're antimicrobial. But what we find is that they actually don't perform as well as we think they will. And simultaneously, the chemicals that they use to impart that property are hazardous to human health. So kind of we don't know that they're doing a good job, and we do know that they're doing harm. So not so good. Perfluorocarbons, actually now known as perfluoroalkyl substances, or PFAS. If you've seen the movie Dark Waters, you might have heard of these chemicals. They're often used to impart stain repellency. These are very prevalent as well. And then many VOCs, so volatile organic compounds, you may have heard about these, often found in paints, in composite wood as kind of the glue that holds everything together, etc. And last is metal additives. And as you can see, as I've been talking for the last few minutes, this gets pretty overwhelming. And we as architects and designers and consultants have quite a lot of opportunity to help make a difference. So what we see in this is obviously there are many hazardous chemicals in building materials. We saw that for sure. It's kind of depressing, to be honest. And what we see, and when we look at biomonitoring studies, is that often these chemicals that are used in building materials are also found in us. So those exposures are happening. So I want to just say, should we be banning chemicals? Surprisingly, the answer is no. So you might hear that chemicals are bad, but these images are just showing people moving through chemicals like water, snow, is water. And chemicals aren't all bad. We rely on chemicals. We are made of chemicals. It's not to say that we should be banning them. And if you take anything away from this lecture, just know that chemical-free is a vacuum. So if you see something advertised as chemical-free, it's complete baloney. It's actually true that chemical-free is a vacuum, and we rely on chemicals for our everyday life. We just need to be careful about what chemicals we're choosing. So that was kind of a little aside, kind of my soapbox to say that don't believe chemical-free when you see it. So coming back to this issue of risk and hazard in buildings, this is really an issue that goes beyond the use phase. So conventionally, we think about, if we're thinking about healthy materials, we're typically thinking about what impacts occupant health. But when we think about materials health, we can think well beyond this, just the use phase. So we can look at production. We can think about who's living adjacent to the place where these chemicals are made. How does that production impact their health? We can think about installation. So who is installing this spray polyurethane foam every day of their lives, and what does that mean for that person's health? You can of course think about the use phase. So paint and the off-gassing of VOCs is a common issue to be thinking about there. And then we can think about the end of life. So what happens when we throw all these materials in a landfill? Construction and demolition waste is a huge source of landfill waste in the US and globally. So it's really important to think about how do these materials and the chemicals that comprise them affect the health of the environment and of people at the end of their useful lives. But I just think it might be a question for you. Why are architects setting chemicals policies in the first place? So why are we even talking about this in this class? And honestly, it's because regulation has been pretty ineffective. So this big blue box represents the chemicals industrially registered in the US. So 84,000 chemicals and growing. This is an old slide at this point, so that number is probably actually higher. But what happened in 1976 was we introduced the Toxic Substances Control Act, or TSCA. And when that introduction came, just those 62,000 chemicals of those 84,000 just assumed to be safe for very little reason. So we just say, okay, you guys are good, 62,000, whoop, you're safe. 1,100 of those have since been regulated through other federal statutes. 600 are now monitored through EPA. 200 have actually been tested, and 5, and actually I think it's up to 9 now, are actually regulated as a result of the testing. So of those 84,000 chemicals, only 5 to 9 are actually regulated. So that's why we're talking about this from the architecture perspective. That's why markets are starting to really question what's in it, how does that affect human health? It's because regulation isn't doing so. And when we look at comparing policy to market action, it's pretty staggering to see the difference. So this, as I mentioned, TSCA, or the Toxic Substances Control Act, was started in 1976. Oh,
I think she's muted.
Sarah, are you back? I think you were temporarily muted.
I think so. Okay, am I back?
You are back.
Oh, thank goodness. My goodness, how can I talk about chemicals regulation if I'm not here? Okay. Great, I will continue then. Thank you, Gail.
Okay, we're good. Thank you.
So between 1976 and 2008, there were some state level policies that were enacted. And then in 2016, I don't know where my slides are going, but in 2016, TSCA was actually reformed, but unfortunately so was our, well, I don't want to get political, but we also had an update to our president, and that meant that implementation has been relatively limited since 2016. But in contrast to that, what we see in the building industry, just as a distinct entity, this is happening in other industries as well, but looking in the building industry, starting in 2004, we have various resources, rating systems, databases, credits in LEED, in various other rating systems, et cetera. And then after 2011, you're probably wondering what happened. It actually got so crowded that I had to make another timeline just to show what happened between 2011 and 2016. And this slide is actually out of date at this point. So much more has happened since this time. So all of this to say, regulation is slow. Markets are driving a lot of the action here. And as you might be thinking about as students coming into the job market, firms are really looking to see knowledge in this area. And it's a really exciting place to start to learn. So I think if you can get interested in this, people are definitely looking for more people coming out of school who can speak this language and understand what the issues are in this area. But I think it's important to bring this back to case studies and how we as architects and designers and consultants can actually start to make a difference, because as these slides that I've shown you have really shown, it's a pretty vast area for change, and there's a lot that we can do. So here are two projects: the Josie Pavilion in Texas by Lake Flato, and you may have talked about the Bullitt Center by Miller Hull in this project or in this class already. But I think these are two pretty exemplar projects that start to get at what I'm talking about when I say healthier materials. So, I just wanted to first say, I gave this talk in another class a few years ago, and a person commented that there starts to be kind of a healthier materials aesthetic. So each of these projects that I'm showing here, the Josie Pavilion, the Bullitt Center, a Google office, I think 2 Google offices, each of these had pretty robust chemicals or materials specification strategies and design strategies. And you can see that there starts to be kind of an aesthetic that starts to form with, exposed materials, a very simplified palette, et cetera. And I would be curious to know your thoughts on that too. It hadn't come to my mind before that question was posed in a class that I was talking in. And since then, I've kind of thought about that more and more. But coming back to the Josie Pavilion by Lake Flato, the first kind of approach that I think is really effective when thinking about healthier materials and buildings is just to simplify. And I think this project does a really great job of that, in part because it's a pavilion, it's a small project in Texas, but I think it does a lot to get at the simplification idea. So you can see from this photo and from other photos of this project that there's a really simplified materials palette that they use as a starting point. And what that did for them was allowed them to, instead of looking to chemistry to solve the problems, they were actually, solving them through the selection of the materials and the craft of the project itself. So as an example, they were using this exposed concrete as a floor. And what they hadn't thought about was, we put additives in concrete to make it level and smooth. But what they could do instead was work with the concrete installer to ensure that the craft of that installation ensured that smoothness and the look that they were going for, instead of putting in the chemical additives. So having that, bringing back the craft in architecture, and rather than solving that problem through chemistry, solving it through craft and design, which I think is kind of a beautiful outcome from this project. And then as you can see, they really prioritize mechanical connections over, glues and adhesives. And that also goes a long way in making a healthier space. Glues and adhesives, as we've talked about, are a huge source of VOCs, of phthalates, of formaldehyde, etc. And then one thing I think is interesting about this project is they relied on passive heating and cooling in a pretty humid climate in West Texas. So it was pretty surprising they were able to do, not surprising, but pretty exciting that they were able to do passive cooling in such a humid and hot climate. And what does that have to do with healthier materials, you're probably wondering. And I think what's cool is that by doing passive cooling, they eliminated the HVAC system completely. And HVAC systems, but we haven't really talked about it much here, are really sources of material issues as well. So duct insulation, adhesives and sealants, binders, cabling and electronic casings. All of these are sources of hazardous materials that we don't need in buildings. So by going to a passive cooling approach, they were able to eliminate that entirely, which is pretty cool. Let's see, I'm trying to advance my slides. There we go. The next project is the Bullitt Center up in Seattle. So what was pretty exciting about this project, well, there were a lot of things, but first, it was a Living Building Challenge project, which meant that they were complying with the Red List, which I don't know if you've talked about in this class yet, but basically says, here's a list of chemicals that are not allowed to come on the project site. And it's a pretty long list, and it's difficult to comply with. So the fact that this project was able to achieve that is very impressive, especially given its scale. It's a full office building in downtown Seattle, or I don't know where in Seattle, but somewhere in Seattle. And why it says reformulate is the architects were able to work with the manufacturers, both I believe of the glulam beams that you're seeing, and also of the sealants in the windows in the curtain wall. They were able to remove the chemicals of concern from those formulations, which is really exciting and really difficult to do. So I think, you know, if we're thinking in order of priority, start with the design, with the craft, with the simplification of the materials palette, and then go to the manufacturer and say, here are the remaining issues, and try to reformulate from there, because it's definitely very difficult to reformulate chemistry on the part of the manufacturer, and it takes a lot of time, which is why I say start early. But what's exciting about this project too is that I believe they had manufacturers sitting with them at the design table. So it wasn't just, you know, an architect calling the manufacturer saying, we need this now. It was more like a collaborative process where the manufacturer came to them and said, here's how we can work with you. And the architect said, here's what we need. And the manufacturer said, here's how we can provide that. And there was a kind of back and forth that became a very collaborative relationship. But I thought I would talk too about some projects I worked on at Arup. So San Francisco Terminal 1, you may have experienced this project, the Harvey Milk Terminal 1. Brand new if you've flown JetBlue or I believe Southwest, they're starting to use this terminal. I'm a total geek and I get really excited every time I fly through there because I'm like, I worked on this. And then there's the East Palo Alto Art Center down in the South Bay, as well as the Portland International Airport up in Portland, Oregon. So starting with the East Palo Alto Art Center, the goal of this project from the healthy materials perspective was just to substitute priority products and priority spaces. So recognizing that there wasn't a huge amount of money to do, you know, full Living Building Challenge Red List free or something like that. This project said, okay, we're going to take a very targeted approach and look at what the priorities are and where we can make the best amount of change. So not only what are the priority products, but which spaces make the most difference. So as consultants, we came up with a list of priority products, said, hey, you should really think about the flooring, about the paint, about the countertops, etc. And then we evaluated where their current product was on kind of a red to green spectrum. So red being bad, green being good. We said, hey, your resilient flooring isn't that bad, but you should really think about a better product for your paint, etc., moving down the list. And what we then did was for each of those priority spaces that I mentioned, we did that kind of evaluation. So on the left, BAU means business as usual. So that's what has already been selected. Where we see red, it means replace. Where we see yellow, use with reservations, and green means great, you're good to go. And what you're seeing here is, so for each room, north, east, south, and west, so each wall, and then the floor and the ceiling. And what we were able to show was that in each of the spaces, they could actually make pretty decent improvements just by the changing out the material selection. So aesthetically, it could remain pretty similar, but there are substitute materials out there from the market, which are healthier for the occupants. And that was pretty exciting. I don't think that this could have been done maybe 5 years ago. And that comes back to the progress that the building industry has been making, as I showed in that slide relative to policy. We're really coming a long way, and we're starting to see that reflected in projects. So what this project is really doing is saying, what are these priority spaces? And within those spaces, how can we make improvements? The next project is the Portland International Airport. And there were two main goals for this project, kind of similar to the previous one, really substituting priority product chemical combinations. So where we saw phthalates in flooring materials, we really wanted to substitute those, for example. So it was targeting these specific chemical product combinations. And the other one is promoting industry transparency, which I'll talk about later. But what Portland was really trying to do was focus first on occupant health, and then where we could focus on installer health, and then where we finally, if possible, start thinking about life cycle health. But occupant health was really the main driver for healthier materials. And so that kind of drove how we prioritized the product chemical combinations that we targeted. So you can see spend and ubiquity. So how prevalent is the material in the interior in the first place? And that was based on cost. How feasible is it to find alternatives for these materials? And then, you know, are they emitting nasty, you know, hazardous chemicals like VOCs or semi-volatile organic compounds? And then other kind of rough approximations of exposure. So is it a liquid that's site applied, or is it within reach of the occupant? That kind of question. And the ones in yellow were weighted more heavily than the others. And so what this allowed us to do was develop a prioritized list of materials that we said, okay, these are the ones we're going to really focus on. And then for each of those, we did kind of a color coding again, where for say flooring, we said, all right, if you're at level 1, you have really big issues across the life cycle from a healthy materials perspective. If you're at level 2, you've got the best available formulation that eliminates highest concern in the use phase. Whereas something like level 4 or 5, you've actually able to eliminate chemicals of concern across the life cycle. And so what we did was for each of those product categories that we prioritized, we assigned a level and looked to how we could maximize the level for each of those product categories. And this project is still in progress. We're in the process of reviewing what materials are currently in use, and it's a really collaborative approach with the architects, and it's a really exciting project to be a part of. So I'm really thankful to be doing that work. And then the last and probably the most simple relative to the other two that I've discussed is San Francisco Terminal 1. So they were targeting LEED Platinum. And what LEED requires from a healthy materials perspective is to disclose ingredients, and then also to encourage the use of materials with more benign chemistries. And we really focused on the first one, the first credit. And you're probably wondering why transparency matters in the first place. Why are we just asking for ingredient disclosure? That seems, you know, kind of simple relative to being able to say our materials are safe. It's just saying what's in it, not making any judgment about it. And what that does is it really starts this virtuous circle, I guess, is a cycle, where an architect asking for materials ingredient disclosure enables reporting on the part of the manufacturer. They weren't going to do that otherwise. They weren't going to just say what's in it without someone first asking for that information. And that reporting enables evaluation on the part of the architect. And that evaluation allows us to do sort of a preferential selection. You know, like in the Portland Airport project, we were able to say, I want a higher level 4 or 5. That's that preferential selection. And that guides innovation on the part of the manufacturer, which improves the product. So it kind of follows in this cycle, just starting with that ask. And just why this isn't even, why this is even an issue, moving that a little bit more detail. Transparency is not required. So when we go to the store, we can look at food. Well, this food isn't that well stocked right now, but let's say we're going to look at peanut butters in the grocery store, and we can look at the ingredients label and be pretty confident that we can compare one ingredient label one to the next. We can assume that they're accurate and that they're comprehensive and that they're telling me everything I need to know, and I can compare them. So if I was looking at an ingredients label and I had an allergy to coconut oil, I could say, okay, this product is not for me. In contrast, in the building industry, the level of transparency we have is really just that much. So we don't know anything about the ingredients that are less prevalent in the product than brown sugar. This is not ingredients for peanut butter. I apologize. But we aren't able to see past the most prevalent or highest concentration chemicals in a given product. And that's why transparency matters so much, is that it's getting the manufacturers to disclose more than what is just required. And these kinds of requirements are common across most rating systems. So WELL requires very similar things to LEED, and Living Building Challenge has an imperative that requires material disclosure, and then of course the red list, which requires, as I said, all chemicals on the red list to be eliminated from the project worksite. But there's some kind of questions about the red list. So this is the red list as it existed in LBC version 3. And there's other groups who are thinking about making red lists for themselves too. So LEED had a pilot one, LEED for Healthcare had yet another one, which overlapped but added to the Living Building Challenge red list. Perkins and Will has a red list. Green Guides for Healthcare developed a list. EPA has a list, and then there's the LBC watch list. And so navigating these lists as architects and designers and consultants who may not be well versed in what these chemicals are is a pretty daunting task. And it's not easy to navigate this world. Even still, even with those lists available, say chemicals red listed by the building industry on the order of magnitude of about 1,200, juxtaposed to the number of chemicals known to pose hazard, which are shown in this outer circle on the order of tens of thousands. So even when we're following these red lists, we're not really making a dent in the chemicals known to pose hazard. So it's not necessarily the most robust approach, but it's definitely one that allows us to prioritize. It's where we are now. I imagine we'll be moving forward with other strategies in the future. And I think where we are in the building industry now is saying we have this space full of hazardous chemicals. We are trying to get more ingredient disclosure through transparency, and then through prioritization, remove those chemicals of highest concern once we know what's in it. So that's kind of the approach as we understand it now. But what's pretty cool is that this issue of healthier materials really translates to future kind of up and coming trends. So who here has heard of circular economy? I think I could have used the poll everywhere question a few minutes ago, but we'll do one right now. So please do the same texting Gail Brager 190 to 37607 and respond A or B to this question.
All right, I think I'm sharing my screen. Sometimes it takes a few seconds for the results to come up. But Sarah, are you able to see my screen now?
Yeah.
Okay. So I have found that sometimes there is a lag. Oh, nope, wait, hold on. Wait a minute. Okay.
Maybe everyone's been scared away by my
No,
bad
GSIs
chemistry.
will invite you to also do this so that we can make sure it is working. And there is, I'm going backwards for a moment because usually my screen will show the directions on top.
Apparently, Gail, they're not seeing the question.
Really?
Yeah.
All right.
Well, go ahead and answer in the chat too if you've heard of circular economy.
All right, let me try something else.
No, this is so great. People have heard of circular economy. Awesome. That's really great to hear. And if you haven't, no worries there either. Does anyone want to? Oh, great.
There we go.
Great. So there's a 60-40-ish split. Does anyone who said yes want to chime in and say what they understand it to be?
And I think you
might
could
be a too tall of an order
if you would like to do that.
But I understand if you don't want to.
Circularity is like designing for reusability or basically reducing waste streams so that everything's reusable.
Great, thanks, Preston. Yeah, it's basically about closing those material loops rather than the conventional kind of linear economy, which is a kind of take, make, waste approach. Circular economy is really about what you just said. So really closing the material loops and reducing waste overall. And you're probably wondering what that has anything to do with healthier materials, but I'll get there. So we're really focusing on circular economy. And so the loops that I'm talking about can really be described by that outer gray circle in which different materials, components, and services of buildings might be made, assembled, and used, and then disassembled, and then recovered and reused. And in the context of a building, this could be done for any context, but in the context of a building, that's really looking at these kind of different layers. So if you're doing this in multiple layers, they're kind of separated by different service lifetimes, as you can see in this diagram. And we're trying to achieve this circularity within each of these layers, within each of these service lifetimes. So where the stuff might be circulated for over 0 to 3 years, the space might be circulated for 3 to 7, etc. And all of this circularity assumes that the materials in each of the layers, which are being cycled continuously, are safe. And so as soon as you introduce a toxic substance into this cycle, you're really contaminating that cycle and ensuring that that toxic substance is occurring over and over and over again, repeatedly, presenting exposures over multiple use cycles. So I think healthy materials and circular economy have great overlap. So where we can use more benign chemistries, we're able to also guarantee that that circularity is not contaminated with problematic chemistries. Arup has been thinking a lot about circular economy. So the company I work for, Arup, this is a circular pavilion that they did, circular building that they did in London a few years ago. And what's cool about this project is that it can be completely deconstructed and reconstructed wherever it wants to go. Unfortunately, I think it's in boxes right now, not being constructed anywhere, but the idea is there. And if you look at the strategies that they use to promote the circular economy, you can see that it really is complementary to and overlapping with a lot of the strategies that I discussed in the case studies. So, you know, prioritizing mechanical connections, limiting the number of wet trades, so reducing those paints, those sealants, those adhesives, selecting materials for reuse, remanufacture, recycling. That's pretty obvious given the circular economy aspect of the project. Less related to healthier materials, but still important, are the ideas of modularity and prefabrication. So I just wanted to point out that there's this overlap between circular economy and healthier materials in so far as you know, reducing the hazardous chemistries in projects that are, you know, potentially going to be reused and recycled over time, and trying to reduce the contamination there. But I think there's this question of, you know, what can we do now as students and as people coming into the industry? And I think this slide sort of summarizes a lot of those strategies that I've been talking about. And we'll share these slides with you if we haven't already. And then I think asking for transparency as soon as you enter practice, you know, if you're tasked with developing a materials palette, you know, you can always add this to a list of questions you ask of the manufacturer. When you're asking the cost, when you're asking the durability, also ask, hey, what's in it? And that will go a long way in improving the industry. And I think too, there's a lot we can do from the education perspective. So there are a lot of great resources out there that start to get at you know, healthier materials education, starting kind of with the simplest and most specific maybe. Center for Environmental Health is a nonprofit, I think, based in Oakland, and they have developed healthier furniture specifications and a tool for selecting healthier furniture. So if you're interested, if you find yourself specifying furniture, maybe you're working in an interiors firm, this is a great resource for that. I mentioned the 6 classes, and there's a set of 6 videos at 6classes.org, which starts to describe those 6 classes and the problem chemicals that I highlighted there at the beginning of the lecture. The 6 classes videos are very accessible. They're designed for designers, so they're also aesthetically pleasing. But yeah, I really recommend those as a resource. There's a database of common products available at ferrosproject.net. And what these are profiles for very common products in the building industry. And it tells you everything that's in it. So if you're curious about what's in acrylic latex sealant, for example, you can go and look at the ingredients that are in it and the hazards that they have. This is a pretty deep dive. I don't recommend it if you're just starting out, but it's definitely a great resource nonetheless. A little less of a deep dive, but still a great resource. Actually, my favorite one is called the Home Free Database. And what it's described as is a cheat sheet, which is my favorite thing. And what this does is for a given product category, it ranks those products from red to green. So this is the product category of insulation. And it's saying that blown-in fiberglass is performing better from a health perspective than mineral fiberglass and boards, fiber bats and boards. And then it'll explain why they've made that determination as well. And then there's, if you're, you know, you have spare time, I guess, if you're sheltered in place and have nothing better to do, there's some great reading materials out there. So if you're curious about how this can be applied to affordable housing, the International Living Future Institute, the folks who developed Living Building Challenge, they have developed a guideline and framework for affordable housing, which I think is great. The Better Building Materials guide came from USGBC, a little bit controversial. It was released and then retracted 2 days later. I don't know if that makes it exciting enough for you to go look at it, but it's pretty interesting history there. And then the prescription for healthier building materials is kind of a guide that summarizes all of the industry knowledge to date for healthier materials. So that's what I have on healthy materials, and I thought I'd jump over to indoor air quality. And again,
Sarah, maybe
start with a poll.
Can you hear
Yeah.
me? Maybe let's take a break and let's just double check the chat to see if people had any questions on what you've done to date. So students, before she shifts gears, anybody want to add a question?
Feel free to just jump in too.
No, okay. Carry on then.
Okay, yeah, it's a lot to take in, so kind of apologies for that. But yeah, if you have any questions that arise, please do jump in, and we'll take time for questions at the end as well. So this nice picture, another poll everywhere question. So what percentage of time do Americans spend indoors? And there's A, B, C, or D for your answer. And just to clarify, this is assuming that we're not sheltered in place, because that will obviously change our answer.
All right, so let's, I'm gonna see if we can, if we're gonna try this again. All right, well, the bad news is that because the instructions are not showing up on top, it doesn't seem like my little Poll Everywhere app might be working.
Oh, I see.
That's what I'm wondering.
Well, feel free again in the chat to throw in your estimate if you want to.
Oh, wait a minute.
Good.
There it is.
There it is.
All right.
Cool. This is great. So 80% seems to be the majority of folks. Let me share my screen again.
And maybe this is more appropriate for the demographic of students because they're better than the rest of us of getting their butts outside.
Yeah, that's totally true. Actually, interestingly, well, students are a sort of specific demographic, but my understanding of the study is that it remains pretty constant in adult ages, regardless of age. But we actually spend about 90% of our time inside. And this goes to show just the extent to which indoor air has such large implications for our health. If 90% of the air we breathe is occurring while we're inside. I think we can think about both health and comfort of that indoor air. So we can think about, when we think about health, what are the time scale of the effects of the health impacts? So is it chronic? So is it occurring over long term through long-term exposures to whatever it is that's indoors? An example of a chronic health effect would be like cancer. Or is it more of an acute, short duration or with an abrupt onset health effect? Examples there would be like allergies or carbon monoxide poisoning has a very immediate effect. In contrast to those health effects, we can also think about more of the comfort aspects or the perceived air quality. So, for example, those annoying odors that we smell when we're next to someone who smells bad, for example, body odor, or some people are very averse to food smells. And while perceived air quality is pretty important to think about, and actually forms the basis for the airflow rates in ASHRAE 62, the air ventilation standard, we're going to be focusing more in this lecture, or this part of the lecture, on the health effects. And with the at the extreme level, an extremely common example of indoor air quality and health comes in indoor stoves in developing countries. And these stoves are used for heating and cooking And they're pretty crude, kind of open flame stoves, which generate a huge amount of particulate and some VOC when cooking. And these have pretty dire consequences. So in developing countries, it's estimated that there are 4 million deaths linked to indoor air pollution. And of those deaths, poor women and children are at the highest risk because they are the ones that are most commonly, in close proximity to those stoves and those cook stoves. And then beyond developing countries, there's also, in developed countries, there's issues that introduce poor indoor air quality as well, which have pretty significant health effects. So energy conservation measures, particularly coming out of the 70s when we had the energy crisis, there was a move toward lowering ventilation rates. But unfortunately, this caused an increase of allergies, of sick building syndrome symptoms, and respiratory infections. And then dampness and mold are another issue where, one study back in 2007 estimated that about 21% of asthma cases in the US are related to indoor mold exposure. And that's actually translating to $3.5 billion of cost. So obviously, indoor air has a pretty significant effect on our health, and there's a lot that we can do to improve it. Just to kind of expand on that thought and relate this back to the first part of the lecture, indoor air quality and health, we find commonly in our homes, in our workplaces and schools, as I've discussed, there are huge sources of hazardous chemicals, and these are can become airborne and affect the indoor air quality. If you're not familiar with some of these terms, asthmagens cause asthma, carcinogens are cancer-causing chemicals, endocrine disruptors interfere with hormone systems at certain doses, and the kinds of disruptions that they cause can cause tumors, birth defects, and other developmental disorders. Neurotoxicants affect the brain, and reproductive and developmental toxicants affect reproduction and development. And just to, even go even further into common indoor air pollutants, because they're so prevalent. We've talked a lot about VOCs and a little bit about semi-volatile organic compounds. So things like stain repellents in carpet, halogenated flame retardants, etc. Each of these is a semi-volatile organic compound, which doesn't go into the air in the same rate, but still can be present in indoor air. Formaldehyde, which is a VOC, is really commonly used in wood products as a binder. So anytime you have something like MDF or plywood, etc., it's commonly used that formaldehyde is the basis for the binder. A few of these other ones, so biological pollutants, things like molds that can be, when a stove is pushed up against the wall and there's condensation occurring on that wall, then the mold starts to grow there and affect the indoor air. Dust mites that can accumulate in carpets. Food smells are another example of biological pollutants. Carbon monoxide, which can be a byproduct of fuel combustion, so cooking stoves that can pose significant hazard in indoor air. Particulate matter we'll talk a little bit more about, and definitely radon as well. So each of these is a different pollutant that is very commonly found indoors and has significant health effects, both acute and chronic. So just thinking a little bit about particulate matter in a little bit more detail, and just to put it into perspective, this slide is mostly for your reference, just to better understand the scale that we're talking about when we talk about particulate matter. So this is a cross-section of a human hair, and then a grain of sand. And then juxtaposed onto that is the scale of both PM10, particulate matter size 10 microns in diameter, and then particulate matter 2.5 or 2.5 microns in diameter. And you can see that they're really quite small, even relative to things that we already consider to be quite small. And it's their size that really contributes to the toxicity. So particles that are less than 10 microns in diameter can really penetrate deeply into your lungs and even get into your bloodstream. And obviously that can have pretty dire consequences. And the PM 2.5 are those particles that are known to pose the greatest risk to human health. So we can think about how we filter those particulates. So outdoor air is typically where we find a lot of particulate matter. And that's why we use filters in our HVAC systems or in our homes, in commercial or home settings, I should say. And you can see on the left here a photo from Stefano showing an unused filter at the top and a used filter at the bottom, just to show even, I believe this was taken from a city with relatively clean air. So even in that context, really, you know, there's a lot of particulate matter that we can start to filter out to ensure that the air inside of our spaces is actually clean for us to breathe. And not all filters are created equal. So the MERV rating shown on the right defines how efficiently particles are removed from the airstream by the filter. And the higher the MERV rating, the better the removal. So I believe MERV 8 is what is typically specified for filters, but some rating systems encourage MERV 13, which starts to filter out, you know, 75 to 90% of PM 2.5 and PM 10, which is much better than the MERV 8 performance, for example. And then just touching also on formaldehyde, because this is something that we can actually do something about. So as I mentioned, it's commonly used for wood binders and resins, but it's also classified as carcinogenic to humans according to IARC, which is a pretty authoritative body in the field. And so with formaldehyde, we're lucky because California has started to regulate it in wood products. So when we're looking to specify wood products as architects, designers, etc., we can look to find CARB Phase 2 compliant wood products and know that the performance relative to, with respect to formaldehyde is pretty good. So just remember CARB Phase 2 for when you're looking at wood specifications. But moving on to another Poll Everywhere question, I thought we could kind of summarize or review or recap what was just said and identify a few of the pollutant sources in this space. So you're welcome to remember or recall from the first part of the lecture where I highlighted some of the chemicals of concern, or you know, some of the pollutants I was just discussing, up to you, but go ahead and click where you think there's some issues in this space. And you can draw inspiration from your colleagues as well.
Is everybody seeing the screen now? That was the smoothest one yet, Sarah.
I know, last one's best. We should keep doing them. Great, so outdoor air is the source of indoor air pollution. That's definitely true.
That was excellent.
Yeah, this is great. So I'm seeing carpet, both in terms of probably its chemistry and then also the dust issue. Bedding, so the foam issue with halogenated flame retardant. The cook stove, yes, definitely true. I'm curious about the tabletops. Does anyone want to comment on that one? I see wood flooring, definitely true. Yeah, this is great. So your determinations definitely agree with mine. Does anyone feel like commenting on what they chose or why, if it's different from anything I've said?
All right,
I'm going to chime in the chat or verbally.
I'm going to hand share back to you, Sarah.
Okay, great. You see my screen?
Yes, perfect.
Great. Yeah, so here I've highlighted a few which are very similar to what you guys were specifying or selecting. So cooktops, so sources of particulates and VOC, and carbon monoxide potentially. Surface coatings, so VOC emissions for sure. Engineered wood, a source of formaldehyde emissions, and then carpet, which could be VOC, semi-volatile organic compounds, or dust mites, for example. But as you guys all identified, there are many other sources as well. So this is all many opportunities for us as designers to start to make change. And there are some trends out there that start to increase the concern for indoor air quality and health. So we're spending increasing amount of time indoors, regardless of shelter in place. That is true. You know, as we're spending more time on our computers, on our TVs, our laptops, etc., more time inside. There's trends in the energy efficiency domain to reduce ventilation rates, which, you know, reduces the amount of fresh air that's coming into our space. And as we saw in the 70s, that leads to a, you know, at an extreme, that can lead to more prevalence of sick building syndrome or allergies, etc. Definitely true that with as we move towards more efficient buildings, energy efficient buildings, we're tightening the building envelope, and that is a great thing. But it also means that we can't rely on infiltration as a source of fresh air. So typically in older buildings, we can rely on that infiltration as a way to get fresh air into the space. But as soon as we start to tighten the building envelope, if we're not providing supplementary ventilation, then we're also losing that source of fresh air. And I don't need to talk any further about the proliferation of chemicals in our environment. I think we're all sick of talking about that. But I think it's interesting to think about what we can do as designers. So I was in a class last week, actually, and the presenter was talking about this idea of a hierarchy of controls. So when we think about the top two, elimination and substitution, what we're really talking about is source control. So can we eliminate the source of that hazard or the problem for indoor air quality? Or can we substitute it with something that is a little less hazardous? Those would be examples of source control. And then there's engineering controls. So ways that we can isolate people from the problem. So that could be through ventilation or filtration, for example. And then the latter two, this was a talk about COVID-19. So we were also talking about administrative controls and PPE, which I don't think are as relevant to indoor air quality. But I wanted to talk a little bit about this study from Harvard in 2016, where they were looking at the effects of source control and ventilation on cognitive performance. So they had three scenarios. They put a population of people into chambers, and they had three test scenarios where the conventional test had one airflow rate and VOCs coming into the space while these people were working and having their cognitive performance evaluated. And then the green scenario had the same airflow rate, but no VOCs. And then Green Plus had twice that airflow rate and no VOCs. And they measured across 9 cognitive domains, which you see here. And what you can conclude from the study is that even in the green scenario, the cognitive performance across the board is improved, which goes to show the impact of improving the ventilation rate as well as reducing the sources of volatile organic compounds in the space, as using cognitive function as a kind of indicator of performance and health. And then also in that study, they showed how increased ventilation or reduced carbon dioxide concentration can also improve cognitive performance. So in these graphs, in each of these 9 domains again, they had 3 different scenarios, one with 500 parts per million carbon dioxide, one with about 1,000 parts per million, and one with about 1,500 parts per million. And you can see, while these lines look to be kind of all over the place, you can see that they can show a distinct downward trend in most every one of these domains. And that goes to show that the higher the concentration of CO2, the poorer the cognitive performance or functioning that we have. So it just makes another case for increased ventilation. And then coming back to this idea of filtration, just to remind you, higher the MERV rating, the better it is at capturing particulate matter. One drawback of both this strategy and the prior strategy of increasing ventilation rates is that they both have energy penalties. So it requires more energy to push air through the higher MERV filters because it's more difficult to pass air through. There's less surface area to pass the air through. So I wanted to touch briefly on some strategies that support both energy efficiency and indoor air quality. So the first would be, this is not an exhaustive list. If you want a long list, there's a paper in the bottom right, which you can refer to. But demand controlled ventilation, where rather than just supplying, a constant amount of air to a room, it's instead based on how many people are in that room. So using a carbon dioxide sensor to modulate the amount of air being supplied. So if there's a huge amount of carbon dioxide being generated, aka a lot of people, that demand controlled ventilation would know and supply more air. Dedicated outdoor air systems, so systems that decouple the heating and cooling load from the air supply. So that's able to, remove or decouple, as I said, the sensible load from the air load. So you can still provide enough air regardless of how much heating or cooling is required. And then displacement ventilation, where, as I've shown in this picture, typically with a typical system where it's supplied from the top of the space, we're assuming it's mixed and we're diluting those pollutants. Instead, in the displacement scenario, we're providing air from the bottom, and that's pushing the polluted air up and removing it from the space. So it's providing fresh air and ensuring that the air around the occupants is fresh, and through the stratification, removing the polluted air. Lastly, I just wanted to talk a little bit about how buildings have a role with the pandemic that we're all dealing with. So there's this great op-ed in the Financial Times. It's pretty brief. Again, if you're feeling like you have some free time, the reference in the bottom right, which is a little hard to read, so I apologize, has a great link to how healthy buildings can help us fight coronavirus. And this is by Joe Allen, a professor at Harvard. And it really comes back to these same strategies that we've been discussing. So, these engineering controls that we can focus on. We hear a lot about the PPE issue, but above that, we can also think about how these buildings are ventilated, how the filtration works, how frequently the surfaces in those spaces are cleaned, et cetera. And I think PPE is certainly an issue that definitely medical professionals are all dealing with right now. But there's also implications on the building design side too that we can think about when we think about COVID-19 and controlling it. So that's what I have. I think we have some time for questions. If you have any, I would love to hear, or just comments or thoughts. Feel free to chime in either in the chat or verbally.
That's great. Well, before we open it up for questions, I'm going to temporarily unmute everybody so we can give Sarah a big round of applause.
Thank you.
Thank you. Thank you, Sarah.
Registrez-vous in the class.
Thank you. All right, we're going to open up the chat now if people have any questions, and I'm going back to mute, and you can unmute while you have a question. Okay, I'm looking at chat. There's a lot of thank yous there, but if anybody has any questions for Sarah, we'll have a few minutes, and she said she'll stick around. Sarah, that was fabulous. Every time you present, I learn something new from you, and I'm hoping that one of the silver linings of this horrible pandemic is that people are getting an increased appreciation for the importance of the air that we all breathe and keeping it clean and the role that buildings can play in that.
The circumstances we're in are getting repurposed and being used for uses that they might not have been originally designed. And, you know, as we look to convention centers to serve as hospitals, they might have really different ways of supplying fresh air and than a hospital would. So I think that's just an interesting kind of design question for us. You know, how can we make sure our buildings can be used in multiple ways if needed?
Yeah. There's a question in the chat. What does it mean to lease materials for buildings? I've actually never heard that term before.
Yeah, so the idea of leased materials is kind of up and coming for circular economy, or definitely inspired by circular economy. And the idea is that rather than having you know, people buy materials to then build their building, say, you know, could the structure be composed of leased materials, which then at the end of their useful lives get deconstructed and then reused in another project as needed? And obviously structure is a pretty extreme example of that, but you could imagine something similar for something like, I don't know, ceiling tile or office furniture, or something that goes into and out of buildings at a fairly regular clip and could be reused and repurposed rather than going to landfill.
Great, let's see, there's some more questions are coming in. What size of chemicals less than 2.5 do chemicals not have an effect on the lungs, if there are any? Since we classify particulate matter as 2.5 micrometers and 10 micrometer chemicals. I didn't completely understand that. Maybe you understand that better.
Whoever posed that question, would you be able to clarify?
Yeah, I was wondering, since like for particulate matter, it was classified as like less than 2.5 micrometer and less than 10 micrometer particulate matter. I was wondering if there was like a lower bound or upper bound where like it wouldn't have effect. Like the upper bound was like sand level, where you couldn't breathe it in.
Oh yeah, that's a great question. So I would have to go read up on the upper bounds to understand where that, you know, where it stops to be, you know, penetrating our lungs, et cetera. But I would be happy to get back to you if that would be helpful for you.
Thank you.
And Sarah, I don't know if you can see the questions as well.
Yeah.
There's one from Jasmine recently. HUD has come under fire for public housing with toxic materials containing formaldehyde. How would this be mitigated? Ooh, that's a big topic.
The whole question of retrofit is a difficult question. Once the elements, the pieces are in the space, the materials are in the space, it's very difficult to, you know, take them out if they're integral to the space itself, whether it's structural or whatever. But I think, you know, increasing the airflow rates, trying to flush out the building while if it's not being occupied would be one approach that could be taken. If it's something that could be removed from the space without too much concern, that's another option. I don't know if you heard about the WeWork issue that came up where they had fill-in booths that had high levels of formaldehyde inside of them. And so what they had to do was just remove them from the space. Obviously, that's different from housing where there might be materials used that can't just be easily removed, but that would be the first thing that comes to mind, and then air flush would be the second.
Let's see, another one. How much does cost become a barrier in using healthier materials in our buildings? Great question.
It's a great question. So I think it really depends on the material that you're interested in. So something like, well, I was just talking to a cable, like electronic cable manufacturer the other day, and they were saying that for those applications, it's between 1.5 to 2 times more expensive to use healthier materials in cable electronic casings than it is to do like business usual materials. So that's kind of one extreme. But it definitely doesn't have to be much more expensive. So the first point I would say is that, you know, do you need the material in the first place? If you don't need it, then it's cheaper to remove it. And that's definitely true of something like stain repellents in carpets. They don't need to apply that material, therefore it's cheaper to the manufacturer to not use it in the first place. so it shouldn't cost any more. Something like halogenated sodium retardant, same thing. They don't need to add it. Therefore, it can just be removed at cost. So I think it really depends on what material you're talking about, but it doesn't have to be an issue.
Good. And then let's just take one last one from Sarah. How feasible is it to implement a lot of these materials or substitutions in retrofits rather than just new construction? Great question, Sarah.
Great question. Yeah. Most of my experience has been in new construction. But I think if you're doing retrofit, it's just as easy, you know, it should be the same kind of selection process of materials, right? You can have the same kind of prioritization, the same kind of use of simplified material palettes, et cetera. The same strategies can come into play for retrofit as opposed to new construction. I would just say being mindful of what's already there. And you know, it's, I guess, you know, trying to not cause more problems with the materials you're putting in. If you see that there's a problem already in the building, you know, what can be done to mitigate further problems, if that makes sense. I'm not sure if I articulated that very well, but feel free to follow up if you want to.
Thank you. Well, again, Sarah, thank you very much. It's a delight to reconnect with you, and I really appreciate you sharing all of your wisdom with us. So with that,
thank you for the opportunity.
Oh, you're very welcome. I see a lot of thank yous on the chats. Thank you for your voices of appreciation, students. And I am now going to end the meeting. Goodbye to all, and we'll see you on Wednesday.
Thanks all.